Hello and welcome. This video is on graphs of functions. In this lesson, you will learn how to analyze the graphs of functions and use a graphing utility to create piecewise functions. My graphing utility I will be using, as always, is this digital TI-83 graphing calculator. Let's first talk about the graph of a function. We are going to be looking at this function notation again, this f of x alongside x here. So if you have a point x comma f of x, x represents the distance away from the y-axis. So when you go over in the x direction, literally you're perpendicular to this y-axis no matter where you're looking at it. Whether it's up here or down there, this is x units away. F of x is the directed distance from the x-axis that's perpendicular in this way as well, similar to y in the same kind of idea. So those are two definitions for you to understand there. Let's talk about something called domain, and then we'll talk about something called range on a graph. Now, domain we've already referred to as all of the x values in a relation or function here. However, on a graph, it's established by spanning all of x such that your function appears either as, and we'll take a look at these, but points represented as a line or a curve, closed dots on a curve or elsewhere on the graph, open dots are not included on the function, or arrows near the borders of a window range, or the disappearance of the function at the end of the window. This last disappearance one is not one that we're going to see on this slide, but on future slides you actually will see it. If open or closed dots do not appear, assume that the graph extends infinitely in that direction. So that's the whole point of that bottom part right there. And then domain is expressed as a set of specific values in an inequality, set of inequalities, or restricted equation. That's what we'll write after we look at the graph itself. So let's say you have some graph. Let's say right here I do some just big graph right there, and maybe it stops right there. I'll do a closed dot. This side there's an arrow, and on this side there's another open dot right here, and it just goes downward with another arrow. Okay, as we take a look at this specific graph, the question is, what is the domain? The question is, the objective for us as far as answering the question is, as we span from the left side from negative infinity to positive infinity, are there any values of x that are not included on this function? So any f of x values that will not work here. And the answer is no, because when I start from the left going all the way to the right, this is entirely continuous. We assume it to be because of the arrow, and this keeps hitting points, and then it hits a point right here and it stops. And you might say, okay, it goes all the way up until 1, 2, 3, 4, 5. So we know there's a scenario here for our domain that says, this is the inequality portion, x is less than or equal to 5. However, there seems to be more points right here. Starting from 5 again, not including 5 in this case though, it continues onward and there's an arrow extending infinitely in that direction. So there's another part that says also x can be greater than 5. But the question is this inequality as simplified as we can make it? Can we simplify this more? Absolutely we could. If x is anything that's less than or equal to 5, or x is anything greater than 5, then x can be anything. So how do we find a different way to write that? We say a case that is all real numbers. So either for all real numbers you can use kind of this symbol. It's like a capital R but with two little vertical lines there to indicate all real numbers. So you can either do that, or as an inequality, just say that x can be anything ranging from negative infinity to positive infinity. So I'm going to use this infinity symbol. It's like a sideways figure 8 in a way. I'm going to do a less than x, which is less than positive infinity right here. Now, infinity is not a number. Infinity is a concept of no bound, of a limitless, a concept of a limitless bound. So x can go forever in that direction, but it can never quite be negative infinity itself because it's not an actual value, and the x has to be less than it. So it's not going to be less than or equal to them. It's just going to be less than. So x can be greater than negative infinity and less than positive infinity. That's the same thing as saying all real numbers. Now, the reason why I point this one out is because there are other notations that we use that are not just inequalities. We also sometimes use this shouldn't say inequality here. This should say an interval, not an inequality. We'll also use things called intervals. Okay. Now, if we do intervals, there's this interval notation that looks like this. You'll use a set of either an open parenthesis, an open square bracket, and or a closed parenthesis with a closed square bracket, like that. One set or the other. And this will indicate whether the boundary point is included as a part of your domain. So if it's open parentheses, that's like less than or greater than, not included. So the value that you use will not be included there. Meanwhile, square brackets are like less than or equal to or greater than equal to, which means included. So if I rewrote this original piece as x is less than or equal to 5, what I would do is I would say, how far left can it go? That's going to be my first number. Now it can go as left as negative infinity. Technically, it doesn't actually reach it. So negative infinity goes on the left. Now can x reach negative infinity? No. So what I'm going to do, negative infinity is not included. On this side, I will put an open parenthesis, like so. Comma. X will be able to go all the way up until 5. So I'm going to place 5 as the other boundary point over here. And it includes 5, so I'm going to use a closed square bracket, like so. So this is a part of my inequality statement. This is the same thing as saying x is less than or equal to 5. So if you ever see that anywhere, or if I tend to write it, make sure you can make sense of that. Now, x has to be greater than 5, so my left boundary point is 5 here. It does not include it. There's an open parenthesis. And then it goes all the way to positive infinity. Feel free, you don't have to put the positive sign, but to really differentiate between that and negative infinity, go ahead. And it can't reach it, so there's that as well. Now, this is just as you originally write that interval. However, what is the true domain? It is all real numbers. So how do you say all real numbers in interval notation? I guess you can do that all real number symbol. However, if you actually had to use interval notation, you're going from negative infinity to positive infinity, and you are not including those ones. So these are not x, y values on a graph. No, this is interval notation to list values for your domain. So that was supposed to say interval there in that case. Let's take a look at like maybe one more. Or how about two more? Let's do another one. Let's say this time it's not actually all real numbers. Let's say instead this time we have something else like, okay, go in here. Now notice that whole open and closed dot thing I was talking about, right? So what if this point is included on that one? And then over here, this point is not included, and it stretches out to there. Okay, here's another interval, and we'll write it both in inequality form and in interval notation. We'll say what x can be and what x can't be. Okay, so in this case, x can be anything that's less than or equal to, let's say that's negative 2, or x can be greater than 3. Okay. So as in interval form, that would be from, once again, negative infinity to negative 2, including negative 2. Not including 3, not including positive infinity. It can also be between those two. So this is interval notation for that same thing. Or it can't be any of these numbers in between. But we're not going to write it in that restricted equation form, because if we did, then you are then you have to list a bunch of numbers, not just negative 1, 0, and 1, and 2, and 3, also everything in between. So we don't do like it can't be inequality. Nothing like that. Instead, you list what it can be in that sense. Okay, what if instead it was the ones that was in between? What if instead I took this line and I made it, or this ray, and I made it a segment like that, and I took this one out of the way? Okay, so in this case, what can it be? It can be between negative 2 and 3, including negative 2, not including 3. And here, if I wrote it in interval form, negative 2 to 3, where 3 is not included. Okay. Now, what if instead of this, I had from negative 2 to 3, but at 1, I had some sort of hull. Now, I'm not showing you the equation of the line that does this. These ones are kind of harder to do. So I took this hull that was over here, and I said, let's place it there. But it includes these ends, like this. What's this one? And what if, oh, sorry, one more thing. And what if then there was a point like that? Okay, now in this case here, what's the interval? I go from negative 2 to 3, but there's a jump there. But at this point, it goes down there. My question is there a value that I cannot choose between -2 and 3? The answer is no. You can choose every value between -2 and 3 like this. So it's still the same as this one was. The range will be different, right, because there's a point that's below that, and there's a different point at x equals 1. That's okay, but this is what your domain would be. Okay. One more to do. If this is not there, and if I go arrows to the left and right forever now, let's go from here downward. Let's make that blue. Sorry. And then the other side. Right there. Okay. A line that's going on forever, but it does have a hole right there. So, let me first do interval notation, because interval notation you'd have to specifically say, well, this one has to go from -infinity up to 1, where neither's included. And then it goes from 1 to +infinity, not included. As an inequality, we don't have to go this complex. We don't have to say x is less than 1 or x is greater than 1. Instead, we can do a restricted equation. X can be any real number except it cannot be 1. So domain is all, and same with range, is all about saying what can x and y be, what can't x and y be. More often than not, you'll probably be saying what it can be when you're referring to inequalities. But if you're referring to something about a jump, a hole, such as that one, or an asymptote, right? We've done asymptotes, same exact idea. We're going to say what x can't be at times, or what y can't be. So referring to range and doing some of those kind of same problems again here, range is all about the f of x, all about the y, and it's saying the set of outputs in a relation or a function. On a graph, they're just as easy to do as domain, so I don't think I'll jump into too many problems with range, except remember that with range, it's not always the same as domain. The other thing is range is really hard to find in equations sometimes. Domain is really easy because you just have to figure out what x can't be. Y is a lot harder to figure out because it is your dependent variable, not your independent variable. So let's go ahead and take a look at an all real numbers case. Let's say I have a cubic function right here that looks like that. Okay. Pretend like it's going outward, not straight up. Your domain and your range are both all real numbers in this case. I'll just say range is all real. Or you can say y goes from -infinity to +infinity. Or f of x. Feel free to put y or f of x. I'm mostly going to put y in these cases because they're not all functions. Or -infinity to +infinity, like so. Okay, let's take a look at a case now where you have a domain of all real numbers, but a range is limited. A lot of parabolas. Let's say, okay, this time I'll give you an equation. Y equals x squared plus 2x. Let's do x squared plus 2x, like that. Okay, this graph happens to, just by my knowledge here, or my perceived knowledge, I hope I'm doing this one right, happens to look something like this. It's parabolic. Okay. Now, you choose values for x. You can choose any value for x. You will always get a value out for y. That's why the domain is all real numbers. Okay? I can go forever to the left and right, spanning on this graph. No issues for domain. Range, however, is all about going up and down. So the question really for range is, how high do I go? How low do I go? Is there a ceiling for y? As I choose values for x, will I ever be restricted on what values for y this can go up to? The answer is no. This will hit up to negative or to +infinity, technically. It doesn't actually reach that. How low does it go? Well, understanding quadratics, if you knew how to find out where this vertex was, that'd be great. If you had the graph, that's even better. You take a look at, say, this dotted line right here. Okay? And you scan. Now, we're not scanning left to right. We're scanning up and down with a thing going left and right. You know, pretending this was like a laser thing, like... I'm having fun with this. Do I still have points? Yes. Do I still have points? Yes. Do I still have points? Yes, 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 and yes. But now, no. No and no forevermore. There are no points down here for y. So my range is limited. The lowest I ever go is -1. And I only go upward from there as far as scanning goes. So what y values can I have? Anything greater than or equal to -1. And of course, an interval notation, including -1, not including +infinity, such as that. Okay? Maybe just one or two more cases. Something with a jump. Something else. Let's do one more, just really quickly, one more where the domain is all real numbers, but range is limited. How about like a sine or cosine trig function like that, where it oscillates between this value and this value here? Let's pretend that was -2 and 2. Okay. Well, domain is all real numbers, but your range goes between -2. Let's say it could include it and 2, like so. So there are functions where range will probably be more often limited than domain. Not necessarily, but just saying, make sure you consider the case that if domain's all real numbers, that doesn't necessarily mean range is all real numbers, and vice versa. And furthermore, once you find your domain in an equation, it's really hard to find it in the range because sometimes it doesn't hit them right at the ends of the domain, so to speak, like plugging in a very high and very low number for x. In one case, the range was limited by the vertex. Let's take a look at a circle. Okay, circle right here, domain and range are actually the same in terms of their sets because it's a circle that started at the center here. Domain goes from -7 to +7, and it includes those, and as does range. Range is the exact same in this case, only for y. Let's see, -7, y, and 7. So there are cases like that, and once again, you can do interval notation there, like -7 to 7 for both of those. Okay? Let's do one more, something with the jump. Recall the jump one that I did before, where before I had a segment, but let's say it was something like that, and it ended there, and let's say there. Let's go up to here. It ended there and there. Okay? Now let's say there is a hole at -1, x equals -1, y equals 2. And let's say there was a point that was down here. So the domain does go from -6 all the way, because we talked about this, to +6. The range does not just go from -3 up to +8, though. What is it? It does go from -3 to +8, including them. However, you take a look and you say, wait a minute, this didn't have a value here for y. Remember, range is about scanning up and down. So I take a look at these right here, and I see, okay, from -3 to +8, I'm good. Oh, not right there. And don't say that it's this point here, because this point is not about scanning left and right. It's about scanning up and down. So here, there is no point to the left or the right. And if I did have a point here, then it probably wouldn't be a function. That's okay. Just kind of letting you know that. So there's a jump there. So y goes from -3. Let's see. Y, how do I say this? Y can be from -3 to 2. And then it can go from 2 to +8. And it can't include 2 in either scenario. Now, I don't just want to say y can't equal 2. The main reason is because it's not all real numbers outside of that. So you could also put -3 to 8, where y can't equal 2. Okay? So you can do something like that. You can have that kind of jump. The final thing, though, we still haven't included a point. Right? There's a point way down here. So whether or not you do this way, whether you do this way or this way, we're still missing a point. And that's this one way down here, -7. Y can also equal -7. So as far as range goes, you got a lot of inequality things you have to refer to. Sometimes you have restricted things, inequalities here, blah, blah, blah. Interval notation is discussed as well. And yeah, so you have a lot of options there, but domain and range are not necessarily always the same. You got to scan left and right and figure out where things go and how things work. In this case, range was a lot more complicated, especially if this was an equation and you didn't have the graph. It'd be super, super complicated. Okay, so let's start talking back about functions again with graphs. The definition, of a function is a relation where every element in the domain is paired with exactly one element in the range. Okay, so that means, and I did do the vertical line test on the previous video, but I'm just going to expand on it a little more, referring to what's written. On a graph, this means there are no points that are vertically above one another, as if an x value shares multiple y values. So let's say I had just some random, kind of graph there. All right. Well, this one, as far as we're concerned, appears to be a function because as we do a vertical line test, remember the lines I was just doing before, this time I'll do them vertically. As I scan left to right on this thing, I just have to make sure that there is no point, there's no x value that's giving me two y values. This seems to be good. This is passing the vertical line test at every single point here, including the assumption with the arrows that they go on forever that way. But if the graph somehow and for some reason went back up and went around like this and did that before it went on, now you can see with this vertical line, it's actually failing the vertical line test. So you can see right here, passes, 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 passes. But once you hit here, it touches at 2 points, a point down here and a point up here. Not a function. It's failing. Here, it's passing through 3 points. 1, 2, 3. And 3, and 3, and 3, and 3, and 3, and 2 again. And then here is 1 again. But if it passes at 2 points or more than 2 points or whatever, multiple values of y for any one x, and it is failing the vertical line test there. Therefore, those are not functions. Now, you take a look at something like this idea right here, but you have a hole, once again, an opening, or any sort of jump. It doesn't matter how big the jump is or not. If you have a hole right there, is this passing the vertical line test now? Yes. How come? Because even right here, this is just somewhere where your function is not defined. There is no value of x, therefore there is no value of f of x. It says for every element in the domain. X equals -3 is not one of the elements in the domain, so who cares what it's paired with? Unless it is in the domain, in which case we definitely need to know what it's paired with. But here it is passing the vertical line test for every x comma f of x value that we have there, or xy value, therefore it is a function f of x. Now, if I had a point that was above like this, where that hole is, where the jump is, it is still passing the vertical line test because even at -3, there's only one y value for this x value. When x is -3, y isn't negative whatever this is, 2 point whatever. No, it's y equals 5. When x is -3, y is 5, despite the fact that it does this. And you might be wondering how these jumps work in equations. They do appear. We'd have to find some equations for that. But no, these things definitely do appear there. So this still passes the vertical line test. This is still a function. If there was this point down here, this was filled up, and this point up here, then this does not pass the vertical line test because at x equals -3, it passes through 2 points, this one and this one. Therefore, this is not a function. Okay, so you take a look at all those piecewise functions that are given to you where they do break apart and they do a lot of those different things. Like, it goes here, hits its end, and then it goes up here and hits that end, and then right here, and keeps going. This is still a function because it still passes the vertical line test. And whenever they make those vertical line tests, they use f of x, and they make sure that it's still a function. It's still 1 point here. It's the one down here. It's still 1 point here, right there, and this goes on forever. So it passes the vertical line test. So what things aren't functions, or where do they appear? As far as more normal looking graphs, well, a circle fails the vertical line test. Okay, and it's not that because outside of it right here there are no points. Remember, those aren't defined for our equation, but these points are. This is 1 point here on this vertical line. It's just right there, -5, 0, and this one here, 5, 0. But once you start going in between, you're getting 2 different points for y for every x value. Therefore, it is not a function. There's one example. Another example would be an absolute value equation, one that goes to the side, meaning kind of like this, absolute value there and there. Okay, also not a function, also fails the vertical line test. Right here, right here, right here. And a sideways parabola even. Last one. Some sort of sideways parabola like that, same idea. That's why square root functions are functions because there's only 1/2 of this thing. It's not 2 parabolas, or it's not 2 square root functions, it's just one of them. This passes the vertical line test. This is a function. So that's how the vertical line test works. And again, a graph that is undefined at any particular x value does not fail the vertical line test. Just because there are no x values here doesn't mean it's failing it. You shouldn't be getting points out, therefore we don't get points out. But anywhere we should only get one y out for every x. Now remember, there is no horizontal line test for regular functions such as these. If I have an upward facing parabola, there are multiple y values, there are multiple x values for any one y value, but that's okay. You are allowed to do a horizontal line, you're allowed to fail this horizontal line test. Meaning if I plug in a value for x and I get a value out for y here, and I plug in a different value of x and I get the same value of y, that's still okay. It can still function that way. There's no problem with that. Okay. So let's start looking at increasing and decreasing functions. Now, I drew a bunch there before, but let me give you kind of the more mathy definitions of them, what an increasing and decreasing constant function is. An increasing function is, now, again, mathy definition, we'll get to the layman's terms. You'll understand it pretty straightforward. A function f is increasing on an interval if, for any x1 and x2 in the interval, x1 being less than x2 also implies that the function of x1 is less than the function of x2. What does that mean? If x is a lesser value than x2, like farther to the left, then your f of x1 will be less than f of x2, which means it'll be a lesser value down low, which means x1 and f of x1 are to the left and below x2 and f of x2. And on that interval, it's said to be increasing because it goes from bottom left to top right, at least for that specific interval. So in layman's terms, as x goes right, as x becomes more positive, f of x becomes more positive. As x goes right, f goes up. Therefore, it's increasing. So you take a look at that, you make sense of it, you say, okay, I think I know what increasing means. That way. Decreasing function. A function f is decreasing on an interval if, for any x1, x2 in the interval, x1 being less than x2 implies that f of x1 is greater than f of x2. So in this case, as x is a lesser value, x1 is a lesser value than x2, farther negative, farther to the left here, then f of x1 is taller, it's farther above, it's higher up, and greater than f of x2, which means we go from top left to bottom right. This is a case of decreasing. In layman's terms, as x goes right, further positive, f of x goes down, becomes more negative. Increasing, decreasing, such as positive slope, negative slope. Now that's just for that specific interval. Finally, a constant function. A function f is constant on an interval if for any x1 and x2 in the interval, f of x1 equals f of x2. Meaning no matter where x1 and x2 are, as long as f of x1 and f of x2 are the same height on that entire interval, okay, then it's a constant function. And that makes sense. We know what constant functions do and look like. They do behave like that. So what I have next are some examples, courtesy of Google Images. What I did was I just pulled some out, and let's determine the open intervals on which each function is increasing, decreasing, or constant. Now, open intervals does mean open parentheses. These right here. The reason why we talk about that is because there are going to be points. In fact, this one actually has the points right here, where it's doing nothing. It, in a way, in calculus, you could say it has a slope of 0, that it's a constant point, but it's not in a constant interval. It's not where the function is necessarily constant. It's where it goes from one to the other. So let's take a look at over here. Let's say it was going from negative infinity onward, and it went to negative 3 right here. This entire time, we're assuming it to be increasing. So it's increasing from negative infinity to, negative 3, not including negative 3, remember. At negative 3, it's constant. Slope is 0 at that point. Then it goes from increasing to decreasing, and decreases all the way down to here. So decreasing goes from negative 3 to positive 1. Okay. Once again, increasing goes from decreasing to increasing. Where else is it increasing? From positive 1 to positive 4. And then it's constant from 4 onward. Now, 4 onward, and I have to actually observe this and take a look, study for myself. I believe you could probably do a square bracket there because it already was constant at that point, and that's where it starts going. If not, go ahead and do the open parenthesis. I actually do have to look that up and clarify that for you. Maybe I'll add an annotation and tell you for sure which way it is. Okay. This one here, now here we're going to have to be, rough and close to it, but decreasing to increasing, hitting that critical point right there. I'd say that critical point's at about negative 1.5. So I'd say it's decreasing at least from negative infinity to negative 1.5. Now, I mentioned in one of the first slides that if there are no arrows here at the end of the window range, it's assumed that it's still going onward. One way you can know that it ends is if there are bullet things there. And I can't always say that for certain. For example, I'm looking at this bottom one here, and maybe I say, okay, maybe this one doesn't go on forever, right? Maybe it's just it's really hard to speak in terms of that. So, you know what? I'll pretend like these ones don't go on forever. I'll put little things at the end because I want to make mention of how else you can determine decreasing or increasing or bounds. So, decreasing from negative infinity to negative 1.5, increasing again from negative 1.5 to positive 1.5. And then decreasing again from positive 1.5 down to over to positive infinity. Right. For the intervals, we are referring to the x values. We're referring to the domain. What are the values of the domain here? Okay, this one, let's pretend like this one goes on forever, this third one. And this time I'll just say them out loud. I'm not going to write them down. Increasing from negative 3 to, let's say, negative 2.1/3, sure. Decreasing from negative 2.1/3 to, let's pretend like it's 0. Increasing from 0 to 2. Decreasing from 0 to, 3.1/3. And then increasing from 3.1/3 forever to positive infinity. Final one, let's say it starts at 0. Okay? Here, it's increasing from 0. And again, I'm not sure if, let's see, 0 would be square bracket here. I gotta think about that one. To 1/2 to 0.5. Okay? That's part of the increasing. Then decreasing from half to, let's say, 2. Increasing from 2 to 3. Constant from 3 to 4. I assume including 3 to 4. Increasing from 4 to 6. Decreasing from 6 all the way to 8. So perhaps also including 8. Like so. You know what? Can you say it's decreasing at 8? Maybe you don't say it's decreasing at 8. I'm gonna err to the side of caution and just put open parentheses for those ones. The constant interval one, though, is a little different, right? Why did you open up? The constant interval one, though, is a little different in that case because if it stops there, then it possibly could be considered to be constant there. All right, now let's look at maximum and minimum values on graphs. Now, this is actually where I'm going to be using the graphing calculator. So first, let's look at absolute maximum and minimum. And after that, I'm going to do the highlight really relative maximum and minimum. Again, on the graphing calculator. The absolutely highest and lowest points of the range that a relation will go when spanned across the entire domain. So let's say that you are looking at some graph. Let's say it's a parabola, like this one right here. Sure. And absolute max and min is saying, how high and low does your range go at the very highest and lowest? And pretty much, if you look at your two values of your range, it's really going to help you. If this value has a y value of negative 4, let's say this was negative 4.5, negative 4, and these arrows indicate that it's going upward infinitely, well, then your absolute min is at y equals negative 4 because it's the y value. So just to make sense, it's range, it's y value, not the x values, not the domain. And the absolute max, I'm not really sure if there is one. Maybe they say none, but really, I mean, at this point, just kind of say positive infinity, just to get that idea. It's approaching infinity. There is no absolute maximum. It just keeps going up forever. So it's approaching there. There may be multiple points that share the same minimum/maximum, and the maximum may be the same y value as the minimum. So if we take a look at two sets here, let's do, instead of a quadratic, let's do like a quartic function. And your quartic function might go like this, and then it kind of has a w like that, and it goes back down. And let's say that these were at the same height. Let's say these were both at about 2.5. Okay, well, that's still your absolute maximum. It's still at 2.5 right there. Y equals 2.5. Absolute min, again, in this case, kind of just goes on forever, negative infinity. The maximum and the minimum might be the same if you're looking at a constant function. So if I take this graph right here and I just go straight across, then your absolute max, pretend like this was y equals 2. Your absolute min, y equals 2. They're both the same in that case. The majority of continuous functions feature their absolute maxes and mins at positive or negative infinity. Now, I don't know if that bullet point is necessary to say because that's not always true, but just saying that you might be approaching one of those two places quite often, in which case you only need to list one of them, especially when it's something like an even-powered function. Now, what if we had an odd-powered function? What if it was something like this that went down, then up, and through? And here we go. No real absolute min except approaching negative infinity. No real absolute max except approaching positive infinity. But maybe these points still have something special that we got to say. After all, we did mention these points in the last slide about increasing to decreasing, right? So these points still mean something for us. These points of, concavity, if you will. These critical points here. This is where we reach what are called relative maxima and minima. So to have a relative max or min, they are the relatively highest or lowest points on a function's graph within an interval of the domain. So again, if you looked back over here, we saw that this went from increasing to decreasing, decreasing to increasing, etc. The intervals at which we're looking at these, the neighboring points, and by neighboring, I just mean from when this thing changes any sort of course of action, decreasing to increasing or to plateauing, which is going to be something else we mentioned. These are certain intervals on this graph, and this, like not this interval itself, but this point compared to the next interval over here. Here, I'll choose this one. This point here has this whole interval from left to right to be looking at, and relatively, compared to all the points around it, this is the lowest point. That would be an example of a relative minimum. This would be an example of a relative maximum, and also this was actually not necessarily a relative maximum because compared to all these other points, these are all maxes, so not necessarily one relative maximum point in that sense. But anyway, so these points have that same idea right here. So if I take a look at kind of this interval here, and then I guess if this arrow says that this goes down forever, somewhere way out there, this is a relative maximum. Compared to everything around it, it is at its highest point, and this is at its lowest point compared to everything else around it as well. I think I used 2 graphs here so I could start drawing on this one. Let me just make use of this graph as to not waste it. But, you might have something that kind of keeps climbing. What if it looks like this? Okay? And because your argument might be, I have no idea what it means to be a relative maximum. What does close to other points mean? Really, it just has to do with whenever these points start changing things. All of these are considered relative maxes and relative mins. So relative min, relative max, relative min, relative max, relative min, relative max. I feel like I'm singing. So these are all relative maxes. And these are all relative mins, despite the fact that you're like, well, these are significantly closer than the other set that you had, and this one is taller than this one. How is that a relative min if it's close to that, and that's a relative max? It's just the points that are as close to it as for which you change shape, you change form. You go from increasing to constant or to decreasing or whatever it is. Now, you might have a graph like, I suppose y equals x cubed that kind of plateaus. It takes this point here, and it plateaus right there and comes back up, okay? By plateauing, I mean it's not quite a constant interval, but it does have its slope at 0 right there because that point is 0, 0 in that sense. So in that case, this is called a plateau. It's not a relative max nor a relative min. And this function never does truly go from increasing to decreasing. It goes increasing to plateau to increasing again. So this is neither max nor min. In fact, I want to take a look at that with the graphing calculator. So I'm going to whip that out now. Let me first see if I have any actual problems I did. Oh, you know what? I do have a problem here. I'll take out the graphing calculator for this problem, for this example here, and we'll go ahead and calculate this max and min, and then I'll take a look at x cubed and see what to do with that one. Okay, it's a word problem here. Minneapolis, Minnesota is the coldest U.S. city in the winter on average. Now, this is my own stuff that I looked up. Right? So this information is accurate as I can make it. The quadratic equation below approximately models the city's historic average temperature, T, in degrees Celsius during its winter season weeks, W. So this model here says T of W, meaning the temperature serving as a function of the week that it's in the year, is 0.1 W squared minus 0.4 W minus 7.7. Freezing point is considered to be 0 degrees Celsius. So as we're looking at this graph here, which you don't always have, I'm going to use the graphing calculator for it. But 0 degrees Celsius is right here. So these winter weeks are all below 0 degrees Celsius on average, which seems pretty cold. Remember, 0 degrees Celsius is freezing point. The calendar year of 2017 begins at week 0. So right here's the expected average temperature at week 0 on January 1st. There are 52 weeks in one full year cycle. The winter season's approximate domain interval is displayed. So this is maybe December 21st area, and this might be about March 21st area, something like that. So here's the winter season, graphed by this function. Which week of the calendar year do we expect Minneapolis to reach its coldest temperature in 2017? Now, you might not necessarily have the graph beforehand, but even if you did, I guess it's going to be right here. It looks like it's going to be week 2. And we're going to see what will the coldest temperature be at that time. So again, if you don't have the graph, here's what we would do. We would find, and by the way, we don't have the y value. I don't think it's at -8. I think it's lower than -8. So let's see what that exact value is. And by the way, there are other ways to do this. This is the vertex of a parabola. So we can use this equation and calculate the vertex using -b/2a and all that fun jazz, which in that case, it does look like it's at 2. Substitute 2 in here and you will get our value. But again, let's look at maximums and minimums on the graphing calculator. I just wanted to use this problem as an example, make sense of what it is we're doing. So I can turn this on. I'm going to go and plot this stuff. Now for t, I'm going to use y, and for w, I'm going to use x. So 0.1 x squared minus 0.4, whoops, that's a negative, minus 0.4 w, x in this case, minus 7.7. So if I want this to look exactly like this graph, I'm going to match it with the same window. I think I put this at about -2.5 and then up to 12.5 for x. And for y, I'm at -9.5, I think, to +2.5. I think that's the main reason why I did that graph, so I can graph it here as well. So there's my window. Let's go and take a look at this graph here. It's going to behave exactly the same as this one right there. We get the same exact look. Now, on this calculator, you have the ability to be able to find this minimum value, not just by moving your cursor toward it. If we go to this button, so I'm close to it there, but if we go to this button here that says trace, above it is an option that says calc. So we'll press second, trace, which goes to calc. We will find the minimum value in this case. And minimum, we're going to search a left bound, something to the left of our minimum value that we know of, somewhere over there. Right bound. And guess, so anywhere in between, press enter, it'll find it for you. It gives us the value right there. Now this, on the calculator sometimes gets weird errors, weird issues like this. The number is truly 2. I feel like it has to do with our window range. If we changed it, it would give us actually exactly 2. So don't take my word for why it does that. But your x value is 2, your w value. It's week 2. Week 2 in the year, around January 15th or so, your average temperature is, and take a look at that, -8.1 degrees Celsius. Now that's just answering the question. But in terms of finding that minimum, you saw what we did there. If we wanted to say find the maximum here for something, I want you to keep in mind that it's only going to find the min or max of where you choose your bounds from. Left bound and right bound. If I have my left bound right here and my right bound doesn't go all the way to the end of that, it's not going to find the highest point on this window. By the way, it won't find the max of infinity because it only does it between your two bounds. So if I right bound right here, this is where it's going to find my max value because this is the highest that it goes. Remember this 8.19 number. Guess, and it'll say 8.19 because that's the highest that it goes between those two bounds. If I could go all the way to the left and right of this graph, it would find the point, I suppose, +2.5. Okay. So anyway, excuse me. So anyway, let's do another graph here. I said I was going to do x cubed, but I realized it doesn't find relative maxes and mins. It just finds your bounds, the max and min for your bounds. So I'm going to go ahead and do x cubed. I'll do something called x cubed minus x. And this will give me a little bit of that hump in the problem, in the graph. I'll do my standard -9.4 to 9.4, -6.2 to 6.2. And so take a look at this one. So it goes down, up, down. I'm going to zoom in a little bit now and say, all right, let's take a look at what we really want to see. Okay, nice, right there. So max and min, relative max is up there, relative min is up there. If you wanted to find them, this is not just as easy to do on paper because this is not a quadratic. There's no real vertex formula that we can do to find it. There's something that you can do, and it has to do with calculus. But you wouldn't see it until you get into calculus. You have to take the derivative and do something with that. So anyway, I'm going to do left and right bound here, and I'm going to guess, and it's going to find my max value. Finds the x value, negative 0.577, and I'm trying to think of what that is as a fraction, if there's something there, or if it's just a irrational value. And there's the y value. So no fantastic x and y values there, so to speak, but hey, there it is. And this graph is symmetrical. It actually has to do with the next thing I'm going to talk about. In that this value down here, I'm not going to bother doing them in. This value is positive 0.577, comma, negative 0.3849. These values but switched. This one has symmetry. Anyway, so to go back to this problem here, let's say that you did know the value of x, or in this case w, when you are finding the minimum. So we know that it's week 2, and they say, okay, so at week 2, what is its temperature? So you take t of 2. It's equal to 0.1. I forgot what the number was. I think it was negative 8.1. So just to kind of show what it is we're doing there. 2 squared is 4, times that is 0.4, minus 0.4 times 2 is negative 0.8, minus 7.7, which is negative 0.4, minus 7.7, which is negative 8.1. Negative 8.1 degrees Celsius is the cold average temperature, and I think that's pretty approximate. You can look that up. I did some research when I first did this problem, so it said something like that, something close along those lines. And there you go. Okay, piecewise functions on a graph for graphing utility. Here's where we're going to do it again. I did piecewise function in the last video without a graphing calculator. Feel free to take a look at that. But a piecewise function, just to kind of revert and say what it is again in blue, a piecewise function ordinarily has multiple equations to represent different intervals in the domain. By their equations, I'm referring to their behavior. They can do different things. They might have the same behavior, like they might both be linear. They might both even have the same slope, but they might cross the y-axis at different points. That's what makes them break apart. But the behavior of each portion of the function only exists on that interval. So as I take a look at this example down here, we have x squared when x is less than 2, 6 when x is equal to 2, and 10 minus x if x is between the values 2 and 6, not including 2. And if you notice here, this thing ends at 6, including 6. It doesn't go beyond that. Piecewise functions have no requirement of spanning across the entire domain. So if this thing says it doesn't, then it doesn't. This goes to negative infinity, but this only goes to positive 6 on this side. So, graphing calculator, here we go. If graphing using calculator, indicate the interval alongside your equation. Use parentheses around both the equation and the interval. What does that mean? Well, I'm going to be looking at the y equals equations in my graphing calculator. I'm going to put parentheses around this term x squared. Then right next to it, I'm going to put parentheses, and right there I'm going to put x is less than 2. That would be my y1 equation. And I can do this one in y2 and y3 if I wanted to. I'm going to show it that way first. I'll tell you one issue with it, especially if you have a color graphing calculator. And then I'll show you a second way that kind of gets rid of that issue. So how do we do that? Here we go, graphing calculator. Let's go ahead and do some of these values. Sometimes these take a while to type in because I have to use the mouse and go over it. So y equals, I'm going to start with x squared, well, parentheses, and x squared. And this is when x is less than 2. Now, how do you do less than? There's a button here, math, above that says test. If I press second in math, here's where your inequalities stand. So x is less than 2. Close that with parentheses. Now, if I just look at this by itself, I want you to see what this looks like. I'm going to have to zoom out again, though. First, I'll go to graph, and I'll zoom out. Zoom. Sorry, I have to do... Oh, you know what? I graphed this thing wrong anyway. It should be 2, not negative 2. You should ignore the graph I'm looking at right now. This says less than 2 and equals 2 and 2 and 6. I'm sorry, I did negative 2 right here. So I'm going to take all these values and shift them. Now what you see is this parabola, and you see it stop, and then you see it go down. Now there's an issue here, and here's where I put this another bullet point. Using dot mode is recommended because calculators might unintentionally connect piecewise functions in connected mode. Might connect things that shouldn't be connected, like this thing right here. Why is this there? So there's a thing called dot mode. If I go to mode here, you'll see that there is an option that asks me to switch from connected to dot. Now you can do this in your y equals equations as well. Notice what's going to happen here. If I'm in connected mode and I go to y equals, you're going to see these little slash guys right here, that just shows that every point's going to connect. If I go to dot mode, right here, all of them are going to change so that they are dots. And I don't really know what intervals they go on, but you see now these are dots. And when I graph this, watch this. It shows dots for the parabola, sure, but it doesn't show it going down, and I think that's the important part. Now, this graph is not just these individual points right here. It's the infinite series of points. But using dot mode at the very least does not allow that thing to connect down there. Okay, so there's one set of points. And actually, I want to go a little bit higher here. Let's go from like, I don't know, I want to keep this 6.2 action going on. Let's go from negative 2.2, how about to positive 10.2? Because I got to get a little bit higher on my graph here. Nothing's really going down below. Taking a look at the graph again, there we go, parabola. Okay, I got to put in the other 2 points. Now, stay in dot mode as you do this, and let's go 6. It equals 6 when x is equal to 2. So here we go, x test equals 2. All right. So this graph right here, you'll see those dots, and then you'll see this dot up here. Now, if I did go ahead and zoomed in kind of around here, one other thing you're going to notice when I'm in dot mode, let's see if I can get all those points. There we go. You notice that this dot, this particular dot right here, I think, that's at 1.95. Notice how it didn't go up to 2. Okay. Notice how that didn't go up to 2 yet. That dot, you presume, is that x equals 2. What if I change this less than to less than or equal to? Go back to test. Whoops. Try that again. Go back to test. And let's change it to less than or equal to instead. Now when I graph it, we're all going to be at that zoomed in look. Let's take a look at where that last point is going. Look, that's at x equals 2. So notice how there's one point that changes everything, and that's where that hole is. That hole represents that I don't have a point at x equals 2 if it's less than or equal to. But if it's just less than, then, if it's less than, then it won't have that. If it's less than or equal to, then it will have that last point. So let's change this back to less than. Okay, back to that graph. I can go ahead and zoom out again, actually. That's fine. Okay, let's go ahead and get the last one here, 10 minus x. So we'll go here, 10 minus x. And this is with x between 2 and 6. Now, if it's in here, unfortunately, you cannot write it as a compound inequality. It won't do anything. So you have to do 2 things. You have to say x is greater than 2. And then in another set of parentheses, you have to say x is less than or equal to 6. All right, let's take a look at that one. Parabola, 1 point right there, and then this set right there. So you see this equivalent looking thing right here. Now, why do those look less like dots? I guess they're just more impacted together, that's all. They're not as spread apart. I got to see what intervals these things go on. But anyway, so there's your graph. And again, this was in dot mode. Sometimes in connected mode, it ends up being okay. Let's take a look at what this looks like if this was on connected mode. Again, go ahead and graph it. So you see that thing going down right there. You see that thing going down right there. You see those going down right there. So you see those issues where those things are connecting. Now that issue is arising for 2 reasons. Number 1, because my dot thing. Number 2 is actually the same thing with, sometimes they do asymptotes on here as well. But the real issue is this. I'm going to show you these. It'll be in connected mode, but it'll be bold. I want you to see these things as they're bold and thick. Actually, I'll just show you this one here. I want you to watch to the right of x equals 2. I want you to watch how this thing traces. It's going to go big here. Now watch this. See that? See how that goes big? Now, of course, the other 2 are coming in. See how that thing goes big? What happens here is it's doing this test. It's literally checking this out. It's saying y equals x squared if x is less than 2. If x is 2 or greater than 2, it's just going to go down to 0. For whatever reason, it just hits 0 because it has to hit the entire domain still. This is all it sees. It sees one equation at a time, and it tries to stop it as best as it can. But in dot mode, you don't see that much of an issue with it because where does it hit the points? Down on the x-axis, but, okay, I want you to watch this thing trace right here. This is not dot mode. I just want you to watch it go up here. It's going to shoot down right here, and it's going to scan across there. So it actually graphs those points. Now, if you want it to not graph the points, you have to put these all in as one equation. Okay. Now, the way that you do that is by adding a plus after every single thing, after every single part of the piecewise function, and then you graph the other ones. I'm going to clear these ones out. Gone. And let's do this with a thick line. Okay, let's go ahead and take a look at the graph. This is in connected mode, mind you. Goes up. Now, take a look. It doesn't go down to 0, but what did it do? It connected the points when they shouldn't be connected. That's why we have to go to dot mode for this. So mode, go back to dot mode, and make sure that when you do that, it will graph just the dots. It's unfortunate to see them as dots, but it kind of looks cool too. So it shows all of these things as one. Yeah, right there. But anyway, they don't connect this way. This is how you graph piecewise functions using a graphing utility in that sense. That's it. So anyway, you could evaluate x at -2 and such. You just have to use the graph they use. Okay, the next thing I'm going to look at here are step functions, the infinite staircase. Step function is a way of kind of drawing a bit of a staircase. It is a piecewise function, but it's a never-ending one. And what happens is it says this, f of x equals, and this 2 bracket thing with x, it means the greatest integer less than or equal to x. So what this means is, let's say we put in f of 1. Well, that number is boom, boom, like that, and 1 goes in. And what comes out? Well, 1, because 1 is the integer that is less than or equal to this number. What if I chose 1.5? Well, that is that, 1.5. And that number, what is the greatest integer that is less than or equal to 1.5? Well, that number is 1 as well. So what happens on these functions is if I do f of 1, I'm going to get 1 right there. And this is going to be working all the way until I reach 2. Once I reach 2, it's going to be an open circle again. 2, f of 2 will be 2, f of 2.5 is 2, and everything until you reach 3. And this open circle goes like here. So this is an infinite staircase that looks like so. I wonder if I can copy and paste this here in just a moment. So anyway, there's that infinite staircase. And you can go negative and positive and 0, and you just go on forever. So as I continue this, looks like I'd be about right there. Okay. Anyway, so it just keeps going. Like so. One more set. Looks good. That's fine. All right. So there's my infinite staircase, and these things are kind of getting in my way now. And voila. So that's what it is. So this is another kind of piecewise function that looks like that no matter what. And these have a real world application to them. And it's actually more common than you'd think. Now, this step function is very specific in that it was just x right here. So I'm going to have to go with it. Let's say that you wanted to buy some songs off iTunes. And every iTunes song, I know they're about 99 cents or $1.29. Let's just say that they're flat rate $1 each. Okay. Now, if they're $1 each, depending on the amount of money you have, this function helps you know how many tracks you can buy. Let's say that, I'm going to zoom in here to really get closer to it. Let's say that in your iTunes wallet, you have some amount of money. Let's say you had $9.80. How many CDs can you buy based on this idea of the step function? If you have $9.80, they each cost $1, you can't buy 10. You can't buy 9.8 songs. You can only buy 9 songs. So take a look at how this kind of works. Let's say X was your money, and Y or F of X or whatever is your number of iTunes songs. Like the number of that you could buy. If you have the amount of money, now negative doesn't really count here, but if you had $0, anywhere between $0 and 99 cents, you could not buy a song, according to this problem here. You could not buy any songs. I shouldn't have erased that. So that's why f of x is 0. Once you have $1, you can buy a song. Once you have $1.50, you can buy a song. You can't buy 2 songs yet, though, not until you have $2. And you can't buy a percentage of a song. You can't buy half of a song or half the track or less quality or anything like that. They're all each $1. And you either completely get them or you don't at all. So if I go to $9.80, which I believe is just close to here, 9.80 or 9.8, it's going to go up to this part right here, and this is at 9 for f of x. Not until you reach 10 can you actually buy it. So step functions actually do have a use and purpose here in the real world. And like I said, you probably notice this much more than you probably do this much more than you even recognize it. So it's always there. And that's another piecewise function type, as I said. Okay, the last bit here is on even and odd functions, and I have some displays to kind of show you what this is about. I'll make this one pretty quick. An even odd function, it's a function whose graph is symmetric with respect to the y-axis is called an even function. So symmetric with respect to the y-axis means if you have the y-axis drawn down through right here, that the left and right side have a mirror image of each other. Or in mathematical terms, it's symmetric whenever you have an xy point on the graph, then there's a negative xy point on the graph as well. Let's say this point is about 1.3, 1. Then that means there should be another point on the graph over here that's negative 1.3, 1. As you can tell, this does not exist on this graph, therefore this is not an even function. Okay, let's take a look at this one over here. This one over here has, apparently it looks like it has symmetry. What if I put the point over here? Let's say this was 1.3, 0. Well, as it appears, this one is negative 1.3, 0, and as is the case for any xy value. Whoops. 0. So this looks to be an even function, and it makes sense here. We know that quadratics can be symmetric. They have an axis of symmetry, and if its vertex is on the y-axis, then it will have that symmetry. Now, quadratic functions are called even-powered functions because it's x squared. Even x to the fourth, a quartic function, is an even-powered function. But an even function doesn't just have to have symmetry down its middle, it has to have symmetry down the middle of the graph at the y-axis there. This one is called an odd-powered function, and this can actually bring us into what are called odd functions here. A function whose graph is symmetric with respect to the origin is an odd function. And what that means is that for any xy value that you have, any negative x, negative y is also on the graph. Now, I made mention of this earlier. This actually might be that x cubed minus x problem that I looked at before. Let's say this point was close to like 0.6, negative 0.3, just to do that. Then this point must be the opposite of x, negative 0.6, positive 0.3, which is close to that. Remember, we saw 0.577 on that. So I'm going to go back to the graphing calculator here, and I'll show you what else you could do. If you're not too convinced just by the look of a picture and you wanted to get some hard proof, what you could do is write down your equation. Now, you'd have to know what the function is, but you could write down your equation. Like this is x cubed minus x. Okay. Minus x. And what we could do is we could look at the table. If I got a table set here, okay, well, I guess I'll start at 0. That's fine. But what you'll see, whoops, not graph. What you'll see in the table are just a bunch of values that you're like, well, that's not of much help to me. What do I need? Well, you need to find out if there's symmetry, meaning if there's an xy value, like this one, 2, 6, which is somewhere up there, then there should be a negative 2, negative 6, and it looks like there is. If there's a 324, there should be a negative 3, negative 24, as there is. So anything that is an xy value, the opposite also has an xy value. Now, does this get flat here, 0, 0, 0? No, what happens is it goes above and below, but we need to change our table change thing. Like how about to 0.1? Now if I go to table, you'll see the points that are in between there. So as it goes up to 0 there, now negative 0.9, 0.8, 0.7, etc. I want you to take a look at some of these values here. So 0.3, negative 0.273, maybe that's right here. Then negative 0.3, 0.273 is up there. So all these points are symmetrical with respect to the origin. So another thing with respect to the origin also means that if you rotate your graph, it looks the exact same way, doing a 180-degree rotation. So I'll show you just that really quickly, then I'll be done with odd functions. Maybe take a look at even functions. If I take this and rotate it like that, you got the same lookout that you did when you first did this thing back originally right there. Obviously, the numbers were upside down, but that's neither here nor there. So that's an odd function. This is an even function for the same thing. The x's change while the y's stay the same. We know that about parabolas. Now, what else can you have? You can also have neither an even nor an odd function. And you can have something that's not a function. The graph of a non-zero function cannot be symmetric with respect to the x-axis. A graph is symmetric with respect to the x-axis if whenever x, y is on the graph, x, negative y is also on the graph. So if I take a look at this one over here, it's not an absolute value graph, but something sort of like it. I have this thing. It's kind of meeting right there, and then it's splitting apart, right? Now, this one's not a function because for any x value, you have multiple y values, like 0, 1, and 0, -1. So if you have a non-zero function, it definitely couldn't be symmetric with this because then it's not a function anymore. It can't flip over like this. This has to be two separate equations, or a y equals but not a function. Now what's this one? What I talked about with this one, this was x squared. All even-powered functions have the ability to be even functions. That's a way to remember it. Same with odd-powered functions have the ability to be odd functions, as long as they're symmetric with respect to the origin. This is a sine wave, so it's neither odd nor even. So what do you do with it? Well, you still got to see if it's symmetric to the origin or to the y-axis. Obviously not symmetric to the y-axis, but this is y equals sine of x. And let's go ahead and graph that, and let's take a look at the table. Y equals sine of x. Let's see if the table reveals anything that we might be able to say. Is this an odd function? 0.09983, negative 0.0998. Obviously, this is missing some values. If you go over here, take a look. 3341665. 3341667. Remember, these rounded again. That rounds up to 5. Yeah, it looks like these two are symmetrical. This one's able to carry more values because the negative sign isn't there. This one's not able to carry as many, but see, those things are symmetrical as well. So a sine, so y equals sine of x, is also an odd function. Meanwhile, y equals cosine of x. Let's take a look at this one because we haven't seen an even function yet in the, I don't want to graph it. Take a look at the even function in the table. From -3 to 3, as x goes from positive to negative versions of themselves, y is the exact same value. Yep, looks like it works out. So there are even and odd functions for you. So this one, once again, reflecting across the origin, is an odd function. So that's it. So what was covered in here, we found the domain and range of functions, how to use the vertical line test for functions, how to determine intervals on which functions are increasing or decreasing. From there, we were able to talk about relative max and min very specifically. We saw step functions and piecewise defined functions, and finally, even and odd functions. So a whole lot on analyzing functions and using the graphing calculator. Fiend!